All right, so today we'll have a conclusion to the topic of relation. You had interesting discussion and also good job in the presentation with some improvement that could be made as well. I hope everybody submitted the group report to Skille, right? And then today I will finish up the very few remaining notions that we've not discussed in partially ordered set. Let me just start with okay. You guys see my screen?
Yes, sir.
All right. So before I continue, is there any questions on the materials we discussed on your focus group discussion? Is there any question on that? No? No discussion? All right. There are a few things here that I won't probably have time to go through one by one. Just to give examples for point one, for example, for this one, can you give the greatest minimal and maximal element of the set? So this is for any set, right? So the relationship in this is the set of all subsets of S. So that is, well, S is the set of A such that A is a subset of S. So that would be empty set, the set of single element up to S, right? Now, let's see whether this Bo set has a least, greatest, minimal, and maximal elements. So least element is an element X of the set S such that X is subset of A or A in one of S. Yeah. So that means here X must be, can anyone guess what X is? What set could satisfy this requirement? What is an element of the set? Let's call it, I don't know, to S, yeah, to power of S. Can anybody guess? What would be a solution for X? What set is a subset of every element of the power set of S?
All integer, sir.
I'm sorry? Will you be a bit more clear, Rafael?
All integer.
Oh, no. So the set S here is any set. So it doesn't have to be a set of integers. For example, S could be a set of A, B, C, D. Or set could be like set of cities in Indonesia. Or a set could be, of course, set could be set of integers, for example, and so on. Now, can we have X? Yeah, regardless of the set S, can we get such a set X?
Is it empty set, sir?
Correct. Yes, that's empty set. So empty set is always the subset of every element of the power set of S, or it's always a subset of every set of S, right? Now that would be this. This makes X the least element. Now what about the greatest element? There will be, of course, set of X in the set here, such that A is a subset of X for all A in here. There will be, should be easy. This one should be the set. Anybody? Should be the set S itself, right? So for any set S, the list with this poset, the least element would be empty set, and the greatest element would be the set itself. Remember, the poset is according to the subset relation. Yeah. Now, if this is the least element, then this is the minimal element, of course. Also, this is then the maximal element. Yeah. If you can find a least element, then that least element must be a minimal element, and also the greatest element must be the maximal element. So there is only one, right? So you could check this as well. Now, there's another questions. What is an infinite? Is there an infinite poset, infinite, yeah, that has a greatest and least element? Infinite poset that has a greatest and least element. Is there any? So, for example, this one. Yeah, this is the power set of natural numbers with this relation. Is this a poset? Is this a poset? This pair? Yeah. Is this a poset? What do you guys think? So is this reflexive? Is this relation reflexive?
Yes, sir.
Yes. Is this relation transitive?
Yes, sir, because subset, right?
Yeah. And what about antisymmetry? Is this relation antisymmetric?
Yes.
Yes.
Oh.
So, okay, then this is a poset, right?
Yeah.
Is this infinite?
Yes, because 2 to the power of a natural number, it could be infinite.
It's not. It's not could be infinite. It is infinite, right?
Yes.
Like this. Let me just put it here as an example. And there is also a set of 2 of them. Uh, 3 of them, and so on, right? So you have like huge infinite set, right? So this is infinite. So what is the greatest and least element? should be the one like similar like before, right? So it's, the least element would be
empty
Yeah.
set
correct, and the greatest element.
to the set 2 to the power of n
No,
of all 2 to the power of n.
you mean the whole set is
Yeah.
the greatest element?
Yes, sir.
This or this?
Ooh.
What is greatest element? Greatest element, yeah, should be x in the power of n such that A is subset of X for all A in here.
Oh, okay.
So which one?
Hmm.
The left one or the right one? The one on the left or the one on the right? The greatest element. This one is correct, right? Because every element here is a subset of the natural number, right? Subset of set of natural numbers, right? Any questions?
I don't quite understand, sir. Why is it natural number?
Okay, what would be an element of the set here? Empty set is an element. The single set containing just one is an element. Single set containing 100 is also an element of this set, right? And also
Yes, sir.
this is an element of this set, right?
Yeah.
Okay, so now I'm looking for an element of this set. Greatest element of this set is an element of this set that is a superset of everything else. What is one element of this set here? That is a superset of all elements here. Is it this? Is it the whole set here, or is it this?
Is it because 2 to the power of n can be every natural number that exists?
No. 2 to the power of n is the set of all subset of natural numbers. The set of all subsets of natural numbers. So the elements of this
Oh, wait. Okay,
is
wait.
not a set of natural numbers.
Oh, I see. Okay. Sir. I understand.
Okay, good. Yeah, then be careful with that, right? So we're talking about the elements of this, right? Good. So I think I'll skip this. Now there is a concept of well-ordered set. Now well-ordered set is well, let me start here. So partial order. You have partial order, you have total order. Total order is partial order plus every pair of elements is comparable. Yeah. And then you have well-ordered. Well-ordered partially ordered, yeah. Well ordered means that it's a total order, totally ordered, plus every non-empty subset. This is over S of n this, yeah. every non-empty subset of S has a least element. Then this is called a well-ordered set. So, yeah, so we have then sort of a three things, yeah. So we have partial ordered set. I think this is clear. So this is must be reflexive, anti-symmetric, and transitive on S, yeah. Okay. And total ordered means that it's partially ordered and every pair of elements is comparable, so it's total ordered. So the sign here is Hasse diagram is linear, right? Hasse diagram is linear or like a chain, straight line, yeah. Now, well ordered means that it has to be totally ordered and every non-empty subset of it has a least element. So when does that happen? If you have a total order, then the Hasse diagram may look like this. Right? Yeah. Is there any other possibilities on how the Hasse diagram of a total order look like? What do you guys think? Is this the only way that total orders Hasse diagram looks like? What are the variations? What is the result of your discussion? Are they all total order in the task B, right? Or was it task 3? Or task 2? Yeah, task 2. When you're looking for R3, are they all total order? Kalush, what do you think?
Yes, sir. Sorry.
Yeah. So when we talk about total order, yeah, how does the Hasse diagram of a total order look like? I give you an
Line.
example. Yeah, it's a line like this. Is there any other variation?
I don't know, sir.
Okay, might be a similar line, but with more element, right? Yeah. Right?
Yes.
Okay. Can I have another variation? Maybe like this. But then from here, it goes up infinitely.
That's also works.
Yeah, okay. It's a total order, right? Also, another possibilities is like this. And it goes down infinitely. The order. Is there any other possibility? What do you guys think? Will be another possibility? There is another possibility, right? Namely, well, like this, and then it goes down infinitely and goes up infinitely. All right. Now, which one is a well-ordered set? Which one is well-ordered? Is this well-ordered?
The middle one, sir.
The middle one is well-ordered, yes. What about the one on the left and on the right?
Oh yeah, that also, sir.
Yeah. What about the two ones? The two examples on the right.
It's not well ordered, sir.
Yes, not well ordered. Why?
Because it doesn't have a least element.
Yeah, it doesn't have a list element exactly. So yeah. Similarly here, right? Not well ordered. So let me give an example. Yeah, a set of natural numbers compared with this relation. Yeah, this is total order. Is it total order or not? Is it no? Anybody?
Yes, sir.
It's a yes or it's a no, Rafael?
Yes, total order.
It's a total order. Yes, thank you. Correct. Yeah, this is a total order. What would be the list element?
And
Is zero a natural number, sir? I forgot.
What is it?
Zero.
Zero?
Is zero or one, sir?
Really? Remember, the relation is this.
Oh, oh,
List element, yeah. So x must be in n such that
infinity.
infinity. You're talking about infinity.
I'm not sure either, sir.
This is this a natural number? No, right? This is
No,
not natural.
sir.
This is not natural number.
So is it n, sir?
Which n? You mean this?
Yeah. Wait, that doesn't make sense. either.
Doesn't make sense because this is not with this is not, yeah. So what is list element? Yeah, list element is, let's see, yeah, x is list element if x is a natural number, and yeah, and y is greater than equal to, sorry, and so I know that this might be confusing with the sign, but I do it deliberately because I want to make sure that you understand. The order is not depends on really the relation. So if and only if, yeah, even if x is greater than or equal to y for all y in here. or if I write it down, it's like this, right? So X is in, let's call it here, this is the relation R, right? And R X Y for all Y is in here, right? So is there such X? No, right? There is no element of X. Sorry, there is no element of the set of natural numbers that is greater than or equal to every natural number, right? Yeah. So this element here is not available now. Yeah. But then the greatest element here is of course 0. Now, some of you might be confused. What is this about, right? So this is different from here. This is another poset, right? Now the list element here is what? This is EB, easy, right? This element is 0, right? The greatest element as well, you can find it, right? No, none, right? There is no greatest element, right? Yeah, you see the difference? By simply changing the relation, you have different answers to list and greatest element. Any question here? No question. Okay. Then which of these two is well ordered? The one on the left here or the one on the right here? Which one is well ordered? Well, of course, the one on the right is well ordered. This is not well ordered. Yeah. Okay. And then I think you should try this. This is a good exercise to try. You find the relation R on Z so that Z becomes well ordered. Now, the well ordered principle can be used to prove induction. Yeah, essentially it says that the statement Px is true for all x in the set S if for every y in S, if Px is true for all x less than y, then Py is. So if we can show that inductive step, then we have a well-ordered induction. So essentially, this is a principle of well-ordered induction, which can be used to show that this statement is true. For example, every integer can be written as a product of one or more primes. I think this is one of our results in number theory, right? Now, I'll skip this because I think you have this already. But let me just discuss this. Yeah, there is another notion called lattice. So a poset is called lattice. So you have partial order. Lattice is partially ordered. Yeah, plus every pair AB, yeah, in the set S has both the least upper bound and greatest upper bound. Yeah, so you have to check this for every pair, right? Now here's an example. So let's have a look at this. So Which one of these four is a lattice? So the first picture, is this a lattice or not? Let's call it, this is picture one, right? So for one, is it lattice or not? Well, this is a Hasse diagram, so it's obviously positive ordered. So we need to check now. Yeah. Is every pair A comma B, so let's say X comma Y in the set has least upper bound and greatest lower bound? Now let's check, right? So let's check every pair, right? So what are the pairs here? The pairs are, well, AB. Yeah, let's start with AB, right? So what is the least upper bound of this? Of AB? What is the least upper bound of AB? Of this and this? The least upper bound is?
Is it F?
Sorry, can you repeat that again, Rafael?
Is it F?
The least upper bound, is it F or is it B? What is the least upper bound of this? What do you guys think? Anybody else? Is it F? What is the least upper bound of this? Okay, let's do it again. For this set, AB, what are the upper bounds? Upper bounds.
Is it B, C, D, E, F?
B, C, D, E, F. And then the least upper bound is then what?
B.
B, correct. Yes. Now, what about the greatest lower bound?
A.
Yes, correct. Good. So this pair has a least upper bound and greatest lower bound, right? Now, let's look at another pair. So we have to check every pair essentially, right? So let's see a pair. What about a pair? A pair AC. The least upper bound is what? And the greatest lower bound is A, right? What about the least upper bound of AC? Is it D? Is it D? Okay. What are the upper bounds? Upper bounds of AC. What are they?
C, E, F.
C, E, F. So then the least upper bound is what?
C.
Yes, very good. So it's easy, right? So what about AD? AD, the least upper bound is
D.
D, and the greatest lower bound is A, and so on, right? I think this should be easy. Now, similarly with BC, BD, BE, and BF, right? BC, the least upper bound is C, and then the greatest lower bound is B. Yeah. Now, what about CD? CD, the least upper bound is
E.
E, correct. The greatest lower bound is
B.
Correct. Yes. Very good. Yeah. So you check this like CD, you have CE. You check for CF. You check also DE. You check for DF, and you check for EF. If every of these pairs, so you have like 1, 2, 3. You have, of course, you have AE, right? AE, AF. You also have like BD, BE, BF. Yeah. So you're like 1, 2, 3, 4, up to, I think, how many of them? To the power of 6, right? So it will be 64 of them. AB, AC, AD, AE, AF. Yeah. And then BC, B, not 64, but rather 15. Yeah, 15. Sorry. Yeah, it's a 15. Yeah, should be 15. So AB, AC, AD, AE, AF, you have to check. If all of them have both least upper bound and greatest lower bound, then this is a lattice. Now, in fact, this is a lattice. What about this one? Again, you check for every pair, then you could see that this is a lattice. So is this. Now, what about this one? Is this a lattice or not? Yeah. How to answer this? Well, try to find a pair of elements x, y such that either x, y has no least upper bound or x, y has no greatest lower bound. Yeah. If this can be found, then the poset is not a lattice. So now let's see. Can we find a pair that has no least upper bound or greatest lower bound? How many pairs do we have to consider? 10 pairs, right? So 1, 2, 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, and then 4, 5. Yeah. Now, let's check the least upper bound and then the greatest lower bound. What is the least upper bound of 1 and 2? According to this relation. This is divisibility relation. Least upper bound of this will be 1, and this is 2, right? What about this? It should be 1 and 3, 1 and 4, because 1 divides 1 divides every element of this, and it's the sorry, not the least. This is the greatest lower bound. Sorry, yeah. This is least upper bound, yeah. Yeah, and so this is 1 and 5. Now, what about this? This pair. Does it have a greatest lower bound? According to that set. What is the lower bound of this? According to this relation. If you find it difficult, try draw a lattice, right? So let's try draw the Hasse diagram, right? What would be the Hasse diagram? How would the Hasse diagram look like? Can you help me? Should be? What would be the element at the bottom? Okay, let's draw the relation then, right? So the relation Rx comma y is such that the pair x comma y such that x divides y. Now, what are the pairs here? Can you give me 1 and
2.
1 and 2, or maybe 1 and 1, 1 and 2?
Yeah.
Yeah,
Yes, sir.
and so on, 1 and 5, and then what?
2 and 4.
2 and 2,
2 and 2, 2 and 4.
4, and then 3 and 3,
3 and 3. 4 and 4, 5 and 5.
5 and 5. So, yeah, how does the Hasse diagram look like?
1,
1, 2, 3,
2.
3, 4, 5. So let's take,
1,
yeah,
1 goes to 2, sir.
all right.
1 also goes to 5. Wait. 1 goes to everything, yeah. Yeah.
Yeah, yeah.
2 only goes to 4. And the others don't go to anything. Yeah.
So like this, right? So,
Yeah.
but we can remove some of them or not? No, I think we're good, right? So essentially what we have is 1, yeah, 2, 4, and then this is 3, and this is 5, right?
Yes.
Now, good. Now, let me just erase this. Now, if you look at the picture, what is the least upper bound of the set here? And greatest lower bound of this pair?
The greatest lower bound is 2.
Are you sure it's 2?
Is it not 2?
Does 2 divides 3?
Oh no. So it's 1.
Yeah, it should be 1. Yeah, greatest lower bound is 1. What about the least upper bound? Do we have an upper bound?
No, you don't have
No.
an upper bound.
So if it doesn't have an upper bound, do we have a least upper bound?
No.
No. So now we find a pair that doesn't have a least upper bound. So
That's not a lattice, is it?
correct, yes. So therefore, this partial order is not a lattice. Yeah. Good. Another example. What about this one? Is this a lattice or not? Can we draw Hasse diagram directly? 1.
Yes. Wait. 1 goes to everything, right, sir? 2 also goes to everything. 2 goes to 4, 6, and 8.
Yes.
4 goes to 8, and 6 doesn't go to anything.
All right. So 2 goes to 4. 4 goes to 8. 2 goes to 6. Like this, right?
Yeah.
Is this a lattice or not?
For 2 to 6, it doesn't have an upper bound, sir.
Correct. So 4 and 6
For
has
yeah.
no least upper bound, right?
Yeah.
So
So
not a lattice. Good. Yeah. What about this? Yeah. Let's have a look at this. Is this a lattice or not? This is infinite set. So this is the set from 1, 2, 3, 4, and so on.
I think it is a lattice.
Is it a lattice? Well, if it is infinite, you cannot draw the Hasse diagram, right? So,
No.
or well, the only thing you could do is you draw a Hasse diagram, but you have like infinite portions, right? So now, therefore, here, just check. Take any pair x comma y in z plus. Yeah. Now, and then you check whether it has a greatest lower bound or whether this any pair.
For x comma y, I think there will always be a greatest lower bound because there's one, right, sir?
There is an upper bound. There is a lower bound. Exactly. At least one is a lower. But what do you think is the greatest lower bound of this?
Does it depend on x comma y?
Yes. So what would be, what is z where z divides x according to this, right? According to the relation, yeah? And z divides y, and z is the greatest of such element. What is z? What do you think is z? Is what is a number? What is an integer, positive integer that divides x and y, and the greatest one at that?
GCD, sir?
Correct. Yes, it is GCD. All right. So now what about this? What is the least upper bound of this pair?
LCM.
Correct. Yes, exactly. So now, is this a lattice?
Yes, sir.
Yes, a lattice. Yeah. Good. Now, I'm running out of time. You could try this as an exercise. Yeah, you could also discuss it with your friends. I think the way you did it with focus group discussion is great. Now you should just try it with this few examples in the slides. And well, you don't, of course, in this case, you don't have to put your discussion online on Scale, but you do it right, with your group. I think it will be helpful. All right. With that, any question?
Not from me, sir. So far.
No. Very good. Sorry, what was it, Rafael?
Yes, sir. No, sir.
Okay, good. What about the rest? Any question?
No, sir.
No. All right. If there's no questions, let me finish the session today, and this concludes the session on relation. I think we'll move on to graph next week. Let's see, right? But it seems that we're gonna move to graph theory next week. Yeah. All right. So thank you very much for your attention, and I'll see you guys next week on Monday.
Thank you, sir.
Thank you, sir.
Okay,
Yeah.
bye-bye.
Thank you, sir.
Yes, sir.